So thanks all for coming along to Lunch and Learn. I'm very pleased to invite Professor Alfred McEwen here today. He's going to talk to you about the previous HiRISE mission, some of the longer standing employees may remember some CCDs that were delivered for this particular mission. And I'm sure we're going to have a very interesting talk here today. So thank you very much, Alfred.
All right, so this will be a brief history of HiRISE. Apologies to Stephen Hawking, and we'll have several other Brits get mentioned here along the way. HiRISE stands for the High Resolution Imaging Science Experiment. It's a Mars Reconnaissance Orbiter. So this started in 2000. NASA headquarters organized a science definition team. Then there was an announcement of opportunity for some of the flight instruments. Other instruments were reflights from previous failed Mars missions. We proposed HiRISE, and in September, they selected Lockheed Martin to build the spacecraft. And in November, they selected HiRISE and XRISM experiments. And launch was in August of 2005. So we had less than 4 years from selection to launch, about 3 years to delivery of the instrument. NASA can't do anything that fast anymore, it seems, at least not at this class of experiment. So here's what our proposal, and here's the typical proposal versus actual what you deliver. But here's what we proposed, and in parentheses of what we delivered. So 0.5 meter primary mirror, check. 14 CCDs from E2V, check. Mass 40 kilograms, well, that grew to 65. In part, that was to accommodate a higher orbit. They realized that the orbit, the 400 by 200 kilometer orbit they had planned, did not work. So it became a roughly 300 kilometer orbit. So we enlarged the telescope in order to still get the 30 centimeters requirement per pixel. Cost that we proposed was $32 million. That was dictated by the AO. They don't do that anymore. It actually turned out to be 2 times higher. And the strange thing is that everyone knew it was going to cost more. Everyone, NASA, Ball Aerospace, independent reviewers, JPL. In any event, we were supposed to initially deliver to ATLO, and that's Assembly Test Launch Operations, in case you use different acronyms here. In January, it was actually December, but we didn't delay launch. Okay, so here's a little bit about the instrument. This is the largest optical telescope ever sent to another planetary body. There's larger ones in Earth orbit. And that was true when we launched, and it's still true, to my surprise. We had a low thermal expansion structure and optics. The detectors are push broom CCD detectors with time delay integration, binning and compression, 14 arrays, 1024 times 128 pixels TDI. And these are arrayed on the focal plane with 10 CCDs with a broadband red filter for panchromatic imaging. And then above that and below that are 2 extra for near IR and blue-green imaging, so that we do color in a narrow strip down the middle. Okay. Here's just a diagram of the instrument with the power supply and remote electronic boxes, the support ring, the telescope, the focal plane electronics, and module in the back of it. And this just shows the ray trace. So light comes in the primary baffle, hits the primary mirror, reflects the secondary mirror, goes through a primary mirror baffle to a fold mirror, then to a tertiary mirror, so the 3 powered mirrors. Then it goes to a second fold mirror, which is attached to a focus mechanism to adjust the focus as needed, and then through the filters to the focal plane array. Here's a picture from Ball Aerospace installing the primary mirror. Don't know who that technician is. Okay, so here's a mission overview. So launch was in August of 2005, Atlas 5. The cruise was the standard Hohmann transfer ellipse to Mars. That took 3/4 of a year or so, half a year, more, no less than half a year. Then we were captured into this long period orbit. Then we used aerobraking, where we dip into the atmosphere to slowly circularize the orbit. That took a few months. Then the primary science phase began in November 2006. And there was supposed to be a primary science phase of 2 Earth years, followed by a relay phase of 2 Earth years, because Mars Science Laboratory was supposed to be launched and be there. Turns out that was delayed a couple of years, but we got an extended science phase there. Now, since then, we've had extended missions. It's still going. It's now been 18 years in operation. And the orbit ended up being as close to circular as you can get given Mars' irregular gravity field. So it varies from about 255 to 320 kilometers altitude. And it's at a local mean solar time of 3 p.m. That varies with the seasons, but as close as we can get it, similar to Earth, sun synchronous, consistent imaging over time. Here's a picture of mounting HiRISE on the spacecraft at Lockheed Martin. There's a big cover over the aperture there that says remove before flight. Very important. So here's our first flight image. It was removed. Here's MRO in the thermal vacuum chamber. HiRISE up at the top there. Here it is on the being hoisted up to the top of the Atlas V rocket. There was launch. There were no solid rocket boosters, so it was a nice, elegant, slow launch. Right, so how does this work? We have these 14 detectors flying in a close formation. Because it's TDI, we need the signal to go straight down the column, so it's not smeared. And an advantage of having so many different detectors is that we could arrange them with a slight smile to compensate for the optics, so that the signal went straight down the TDI column for every one of them. With the new detectors that are bigger, that's great in many ways, but it's a new constraint on the design of the optics. So it's push broom imaging. The spacecraft orbital motion pushes the sensor projection across the ground. We have to identically match the orbital ground speed for line integration, which is about 3.2 kilometers per second. The pixel scale ranges from about 25 to 32 centimeters per pixel, maybe a little more if we're pointing off to the side for stereo, for example, for targeting. And the integration time during the motion of a single pixel is 0.0001 second. So the challenge here was, how do you get enough signal to get a decent image with that short of a line time? And the answer is TDI. We image the surface 128 times and add up the signal. There was a lot of worry about this in terms of the spacecraft jitter. Is it really going to be stable? But Lockheed Martin actually did a great job with that. It's been a very stable spacecraft. And the IFOV, instantaneous field of view, is 1 microradian. Nice and simple to remember that. The field of view 1.15 degrees with 20,000 pixels from the 10 detectors. So here's what a full image looks like, reprojected. We have the color strip just down the center there. That's we couldn't, really we'd want to have color over the whole array, of course, but that would have meant flying 30 CCDs, and the power requirements and the thermal burden of that and so forth was more than we could handle. So JPL wanted us to even get rid of this little bit of color because they're always trying to make you descope, but we managed to keep it. And just to go back, it's very hard to show the whole image at full resolution. You need a big wall to do that. But here's just a little sample of it at full resolution. But the whole image has that scale. Sorry, the slide's a little bit saturated. Okay, so our biggest instrument challenge was speed. We move over the surface at 3.2 kilometers per second to image about 1 foot square pixels on the ground. And my analogy for the general public is this like imaging coarse sand grains on the road while driving 125 miles per hour. John Travolta says speed kills. It almost did kill us. This was our biggest challenge, was how to read out and process this data. And our biggest problem throughout flight has been error in the readout electronics, in particular the analog to digital conversion and errors we get with that, which have gotten worse over time. Okay, so where are we as of a few days ago? More than 93,000 Mars images have been returned, 51 terabytes of raw data, 53,000 gigapixels. That sounds like a lot of data, but that would cover, if all unique, only 4.7% of the Martian surface. And the unique coverage is more like 3% maybe, because we do repeat imaging for change detection and for stereo coverage. And we've, I think that's wrong, it's 8,000, not 78,000, 8,000 planned stereo pairs completed. I typo there. And I always like to show a very recent image, just to show you we're still operating, still getting great data. Here's a very small piece of an image acquired last week, some light tone layered sedimentary deposits. We haven't done a great job of tracking how many publications were really based on HiRISE data. The easy thing to do is use NASA ADS and see how many papers mention HiRISE in the main text, some of it being peripheral, but nevertheless, this shows you there's over 2,000 refereed publications that at least refer to HiRISE. Many of them are based primarily on HiRISE. And you can see the distribution over time. I think 24 is incomplete there. Okay, so let me show you some of our favorite images, greatest hits, like an impact crater. By coincidence, when we arrived in the final orbit, the low altitude orbit, was about the same time that the Opportunity rover arrived at Victoria crater. It landed to the north, but it had arrived at the edge of the crater, and one of our first images was to attempt to image the rover. And it was a big thrill to actually get the image on the left here. I'm sorry, I can't point very well here, but you can see the rover, and you can actually see the shadow of the pan cam that sticks up there. And you can see the trail of the rover, and you can see where it stopped. And I looked at that and went, wow, we can spy on this and see exactly what it's doing. And then, although Mars Sample Laboratory was delayed, the Phoenix mission launched in time for during the prime mission, and they had picked out a landing site already. We imaged it and said, look at all those boulders that you couldn't resolve before, and they changed their landing site. But then we actually tried something that I laughed at when I first heard about it, which is, oh, let's try to image it descending on the parachute. We actually succeeded in imaging it. It's actually, you can barely see it there. It looks like it's landing in that crater. That's an illusion. It's actually some 20 kilometers in front of it. And we actually, at the same time that it was descending on the parachute, the heat shield was in free flight. It had been released and was free flight, but hadn't hit the surface yet. I noticed online just this morning that E2V had a press release when this came out and said, that was our detector that took this picture. So then we had to do this again for Mars Science Laboratory, and we did it for Perseverance as well. But for Mars Science Laboratory, we're much closer, and it's a bigger parachute, so we got a pretty spectacular image of it. I like to show this before and after. Oh no, it crashed. Everything crashed from MSL except the rover itself was gently lowered to the surface via the sky crane. And a few images of the parachute. We can see it shifting around in the wind. And once we saw this, we understood, we were puzzled by the fact that we could still see the parachute from Viking Lander 1 from 1970 something. Shouldn't it be covered with dust? You know, we were puzzled by it until we saw this. Oh, it blows around in the wind and it kicks off the dust. We found all of the successful landers and rovers pretty easily. And then we searched for the ones that weren't successful. Mars Polar Lander was one of those. We were never able to find that. But that's at a polar region where all of the albedo changes from the landing get painted over with the seasonal frost and dust every year. And I don't think we'll ever find that one. We had a lot of trouble finding Beagle 2. And but I never gave up hope because it was equatorial and the marking should still be there. And this was found, a suspect was found by somebody who used to work at ESA, but just via general public, saw something he thought was it. And he put in an image suggestion. We have a public image website. Anybody can suggest images. He suggested that, and when we got that image with now the lander in color, we also saw not only did the color help, but we saw that there were bright spots that moved around with each image. Well, we're looking at a different angle, so those are specular reflections off of different solar panels or the main lander, and we could see like 3 of those specular bright spots. So this told us a lot. We also found the parachute and cover, and this told us that really it landed successfully and began to deploy. We don't know if it completely deployed and opened all of its solar panels or what happened after there, but it basically landed successfully. Another highlight of HiRISE is that prior to HiRISE, the Opportunity rover was stuck for 5 weeks in what they called purgatory. These were these cross drifts of these sand dunes that are trending north-south, and cohesionless sand, and they spent 5 weeks trying to figure out on the ground how to get unstuck from that. But they figured out from this that you can identify those places where the sand is loose. And with HiRISE, there were images then to see that. They were able to plot a route to drive all the way from Victoria Crater to Endeavour Crater without getting stuck again. And then a comparable story from Curiosity. They designed the wheels to be able to land safely with a sky crane. They didn't think about driving over bedrock. Turned out the wheels were a little bit too flimsy, and they started seeing holes in the wheels and went, oh no. But again, using HiRISE, the geologists were able to interpret. You can't resolve all of the little bedrock facets that are causing these holes, but you can interpret the geology in order to say, here's the way to drive, and they've managed to avoid further wheel damage with the MSL, which is still going. It's gone a lot further than what's shown in this picture here. So in addition to straight images, we also acquire stereo images. We have to point the spacecraft on different orbits in order to get the base to height ratio. But this has worked out well. We have to try to get them quickly so that the illumination angles don't change much, or wait a Mars year typically to get the same illumination angles. But we've gotten thousands now of stereo pairs. And with these digital terrain models, we can do all sorts of fun things like reproject images, analyze the structural geology. If you look at the rover, for a long time when you looked at rover images, you never saw anything rough like this with steep slopes. That's because they picked all the flat boring places. Curiosity MSL is an exception, where they landed where there's some steep topography. Here's another interesting feature in Valles Marineris. There's this mound in Ganges Chasm. It's composed, it's sand with a high proportion of polyhydrated sulfates. There's a lot of water in that, actually, tied up in the minerals. There's part of the full image and a blow up on the color. Looks pretty interesting like this, but when you reproject it using the stereo DTM, here's what it looks like from the ground. And that's no vertical exaggeration. Those slopes are really that steep. And there are flyover movies as well using DTMs, but I didn't want to attempt that here because it never works right. But if you go online, you can find lots of flyover movies. So our color data is quite interesting for showing the bedrock diversity over the places that are not covered by sand or dust. And this is one of my favorite images because I was going to a meeting in JPL once, and the building was kind of a maze. And so I had to stop and ask directions. How do I get to this room? And the directions included, turn left by the painting. They thought this was a painting, so it made my day. These are enhanced colors, but the bluish colors are typically the unaltered mafic minerals with pyroxenes and olivine. And the warmer tones are typically water-altered minerals such as clays. Here's a very interesting image that we caught early on, and we haven't seen this anywhere else, I think. We see lots of alluvial fans on Mars. They're typically at the edge of what would have been the body of water, or where the water was deposited, maybe a delta, maybe a alluvial fan. But this one is in a location where it seems to be sublacustrine. In other words, the sediment flowed underwater to the center of the basin and was deposited. I don't know if there's any way to turn off the front lights here. That would help without making the whole room dark. Well, something else we were really excited to see was, nope, it's all or nothing, okay, was this columnar jointing. And in fact, it's two-tiered columnar jointing, which on Earth, the way you get that two-tiered columnar jointing is if you dump lots of water on the lava while it's cooling. And this is a crater that's inside a channel. So this is more evidence for water on Mars. And we discover water on Mars often, several times a year. It's not per month. Here are some initially very puzzling features we saw over the surface of Athabasca channels, which initially was debated whether it was water or lava from HiRISE. We decided it was definitely covered by lava. It could have been water floods earlier. But what are these features? Why did they form like this? They look a little bit like pingos that form in Iceland, where lava flows over water-saturated ground, except they have this strange pattern to it. And we decided that this formed when the lava was draining away. First it filled up, must have been wet ground or ice-rich ground. As the lava was draining away, it reduced the pressure, and then these things erupted. And so you have this pattern of flow along with these little cones. But let me do a zoom in sequence of this same area of Mars. So this is an image from the context camera on MRO, about 5 meters per pixel, showing a broad area here. Some impact craters, lava to the lava, both north and south part of this image. You can zoom in, oops. Can't go back, okay. I zoomed in on the CTX. Here's zooming in on HiRISE at one level. And you start to see the textures on the lava flow in the upper part of this. And then you can zoom into another level, and here are these strange spirals. And this was seen by a student at ASU. We're from the University of Arizona. They're our rivals. They saw it before we did, but there's so much data that's not surprising. And interpreted these as lava coils. So you have pieces of lava that are shearing past each other, and it twists the lava up into these forms. The layering on Mars was of great interest, and what we saw was that a lot of it is actually periodic, sort of like the polar caps are periodic. And this has like two periods to it, long and short, which may be related to climate cycles from the past. We have some similar rocks on Earth, like in Utah. Here's the HiRISE team in a HiRISE team meeting. We like to go to fun places and look at the Mars analogs. Here's a picture of jumbled blocks in Candor Chasm. And these are layered blocks, and this was very puzzling at first, but I think the interpretation I like is that it's a landslide deposit of these fine layered deposits that we see elsewhere that fell in here and made this jumbled mess. We see lots of evidence for past glaciation in the mid-latitudes of Mars. Not at the poles, it's too cold for the ice to flow there apparently, or to flow enough to make these sorts of features, but in the mid-latitudes, there's not ice there now, but there was. And this is just another zoom sequence, starting with context image on the left, zooming in again to HiRISE, and zooming in one more time with HiRISE. So you can see, you see very different things at each scale. We've seen a zoo of features on Mars. This one, everyone agrees this one looks like an elephant, so that was easy. The next one, I thought it looked like a bear. Not everyone agreed with me, but as PI, I got to call it the bear. Okay, so one of the really fun things that we somehow weren't expecting was all of the present day activity we would see. MRO is perfect for this because not only do we have the very high resolution, you see more change at the higher spatial, at the smaller spatial scales, but we have this sun synchronous orbit and the ability to target, point off nadir, do repeat imaging. And so there's lots of current activity on Mars. It's not just the moon with a dust that blows around, which is sort of what some people envision of Mars. One of these features that changes are new impact craters, and we've now seen more than 1,200 new impact sites on Mars. Here's just an example of one of these. They typically have a blast pattern from interacting with the atmosphere that blows away the dust, and then there's an ejecta pattern, and there's a crater. Some of these are special. We started seeing craters that actually exposed this bright white material. I thought, that looks like ice. And by monitoring these sites, we found that it disappeared consistent with models for sublimation, the way ice should behave. For the biggest ones, the CRISM infrared spectrometer was able to confirm water ice here. And these occurred further south than we knew ice to exist near the surface previously. Even and further south than the gamma ray spectrometer, which can only see to a depth of about 0.5 meter. Ice is a critical resource to future human explorers. You need ice to make water to drink, to make oxygen to breathe, to make fuel. That's the most valuable stuff out there, and that's why there's so much interest in the polar ice and the moon, but this is, unlike the dirty ice on the moon and not very much of it, this is massive quantities of very clean ice. It's only bright because it's more than 95% pure ice. It only takes a little bit of dust mixed in with it to make it dark. And also the rate that it sublimates and disappears tells us about the dust content as well. So, and this stuff is shallow. So, I mean, an astronaut could walk over this and kick at the soil and expose water ice. We had a new record center in terms of the size of a new impact crater. And if we had to pick we had to choose, we were controlling the impact and said, where do we want this big crater to hit? This would have been the perfect spot to pick. It was about 35 degrees latitude in a place where we saw geomorphology suggesting subsurface ice, but we had not directly detected ice. You needed, no doubt, to have a bigger crater to detect the ice that would be deeper, closer to the equator. And sure enough, we did find it. This is at just 35 north latitude. What's the latitude of us here now? It's higher than that. Anyhow, this was also the strongest seismic event ever recorded by InSight and told them a lot about the interior of Mars. We knew about dust devils on Mars, but we got very nice pictures of them. This is one we call the serpent dust devil. The bright white thing is airborne, and the dark thing is its shadow on the surface. We thought this one was impressive. Then we saw another one that then we could, from the shadow, reconstruct what it would look like from the side and how tall it was. It's about 20 kilometers high, dust devil. There's Mount Everest to scale next to it. So if you were on Mars looking at one of these things, you would be very impressed. However, unlike the movie The Martian, it would not come destroy everything. It's the atmospheric pressure is so low. They look scary, but they're very low density. There are active sand dunes all over Mars. We suspected some of them might be active, but we hadn't directly seen that prior to MRO. Now we've been tracking these, and we keep finding pretty much everywhere there's dark sand dunes, they're active. The activity of the saltating sand kicks off the dust. That's why they're dark. And they're especially active in some places, but pretty much everywhere on Mars they're active. We've been tracking these dust avalanches or slope streaks on Mars for some time, but this one, first detected by CTX in the lower left there with before and after image, looks strange. And so when we got the HiRISE image, we discovered there's actually a new impact crater at the top of that. So the impact formed, and that destabilized the slope and the dust to make this fat slope streak. Most of them are much narrower than this. Here's another very, very active place. This is a steep polar cliff in the North Polar layer deposits. This is a perspective view. There's no vertical exaggeration. There's slopes up to 80 degrees. And in a certain time of year, early spring, early northern spring, we see these active avalanches, or we see dust clouds. And in fact, they're so common, you can take one image with multiple avalanches. How often do you see an active avalanche looking out the window at Earth? These are incredibly active every year. And we think that this is related to slabs of ice that break off in the spring when the sun first illuminates as it goes from being extremely cold to warming up to its peak temperature when the sun rises just a little bit above the horizon. And that causes these slabs to break off. We don't want to establish a human colony at the base of one of these cliffs. That would not be good. So gullies have been a topic of great interest. They were first, these fresh-looking smaller gullies were first detected by Mars orbital camera. Very big deal. They announced, water on Mars today to great press coverage. We started monitoring these and got lots of nice images of the gullies changing, but we found something not many people expected. They're all active in the winter when there's, in fact, CO2 frost on the ground. Now, the CO2 frost buffers the temperature of the atmosphere and the surface to the CO2 frost point of something like 150 degrees Kelvin. Is that right? Or is it? Yeah. That's way too cold for liquid water. So it's definitely not liquid water that's causing this activity. And we've seen more and more of this. There's a lot of this activity, enough to explain all of the sharp-looking gullies, although we can't prove there isn't liquid water affecting some of them. Another fun thing that was puzzling at first were these linear gullies, they were called. Just a straight channel plowed down the slope, and then often pits at the base of it. What caused that? Then we actually saw ice blocks sitting in these channels. And that's it, the ice block. And what happens from lab experiments too is that the CO2 ice is sublimating and sort of blowing out from underneath it, blowing sand to the side as it goes downhill. Okay, after the gully thing, we debunked the idea that they were liquid water today. We discovered something else that we call recurring slope lineae. And these form and grow before our eyes in the warmest time of the year, the opposite of the gullies, which are the coldest time of the year, and including equatorial latitudes. And they form gradually, fade, and then reform in multiple Mars years. They typically extend downslope from bedrock outcrops or rocky areas, sometimes associated with small gullies. So they are active in seasons when the peak temperature exceeds about 250 Kelvin. The melting point of pure water is 273 Kelvin, but Mars is salty. That depresses the freezing point. That's a very reasonable temperature to have liquid water on Mars today. And it looks like seeping water. There are features in Antarctica called water tracks that look very much like this, except the water tracks extend down to very shallow slopes. Once we started studying these and getting topographic data, we discovered that these things, they all stop when the slope gets to about 29 degrees. That's the dynamic angle of repose for dry granular material, and that can't be a coincidence. They are often associated with these small gullies, and I'm still unclear on whether this activity forms the gullies or something else formed the gullies, and they just follow those. But these are now equatorial gullies, so it's not CO2 frost carved gullies. There's still a lot we don't understand. Anyhow, these RSL caused big excitement with NASA again, and they decided to have a press briefing when the first author and I were both at EPSC in Nantes, and we were surprised to learn we're having a press conference, and we're even more surprised when we heard them rehearse and what they were saying. That's John Grensfeld, who was the associate administrator at the time, and Jim Green was the planetary science division chief there. Mike Myers was the Mars program scientist. And they made a big deal about how definite evidence of flowing water on Mars today. I had to cringe a little bit because it really wasn't definite. This was before we did the detailed topographic studies, but all this attention led to some people having fun. It was about the same time that the movie The Martian came out, and so somebody decided to write, bring Watney a straw. He didn't have to do all those crazy things. He could have just dug in the backyard to get water. Like this one, Martian natural spring water, only $2 million per bottle plus shipping. It's like, actually, now that we know what Mars sample return costs, I think that's an underestimate. Okay, here's an illustration of the terminal slopes being identical to dune slip faces slopes. And okay, now we found something else of interest here. We found these scarps with bright, icy-looking material in them, and CRISM confirmed that it's water ice. And there's a close-up on some of this. It's over 100 meters thick. This is apparently almost pure water ice, 100 meters thick, extending to within maybe a meter of the surface. People get excited about water in the polar regions of the moon, which is a small percentage of stuff at 40 Kelvin or something hard, very hard stuff to Mars. It's easy. The water is right there, lots of it. Okay, we've also had lots of fun watching the dry ice, CO2 seasonal processes. So this is a series of images of the same sand dune and how it looks at different seasons as various features form and disappear and change over time. I'm not sure how much I explained. Oh, here's one image where the London Times Daily Express of London announced trees found on Mars. You can clearly see these things are sticking straight up, right? Right? Mm. I prefer to show the image like this. They're starting at the high points and flowing downhill. So these are mass wasting features that expose dark sand in contrast to the bright CO2 frost. We even see a little bright puff of dust there that we caught one in the act. Okay, David Bowie said there were spiders on Mars. He was right. Here they are. These are dendritic features that flow uphill to a central position. And the theory is that this is from, you have this thick layer, meters of CO2 ice that forms seasonally. And then it starts to sublimate. It's translucent. So the sunlight penetrates through it to the bottom, warms up the dark material below the ice. That then sublimates the CO2 to make gas, which then flows to where it can escape and forms these features. That's the theory. We actually have seen some features that may be new spiders in formation. It's, as a geologist, I can tell you, it is so much easier to understand an active process when you can actually watch it happen. Just looking at the ancient geologic record and trying to figure it out, you get all sorts of crazy theories and nobody knows for sure until it happens and you can see it. So the things like the Mount St. Helens eruption was an aha moment for, now I know what happened at all these other places around Earth. The south polar residual CO2 ice cap changes dramatically. You have to look at this a while to convince yourself you're looking at the same place on Mars even, because there's so many changes over 6 Mars years. And it looked to some people like the ice was disappearing because that's the obvious thing that changes, but there's actually new ice being deposited in the flat areas, new frost, so it's just moving around. We also imaged Phobos in color. That was fun. And Deimos. Put Deimos in here. Deimos isn't as colorful. All right, so we produced captured image releases every week. We now have over 2,000 captured image releases available on the website, and the selected captions have been translated into 28 different languages, and this is all by volunteers who speak that language and English and are able to translate them for us. And I mentioned HiWish already. So anybody can go suggest an image, including the ESA engineer who discovered Eagle 2. And so we called HiRISE the people's camera. Everyone to participate, be able to target HiRISE, and we process and release our images quickly. And so power to the people, John Lennon. What's the future of HiRISE? MRO has fuel for another 10 plus years. We were able to really load up on fuel. That was great. But 2 of the 14 HiRISE units have failed. It's not the CCDs that failed. The E2V CCDs have been great, but it's the electronics that control the CCDs, the ones that we really have to process a lot of data in a hurry. And one failed in 2011, Red 9. That was on the edge of the field of view, so it just shrank by 10%. That was not so bad. Then in 2023, one right in the middle failed. That was more painful. However, it was in the center where we also had the IR and blue-green images, so we can use those to plug that gap. Slightly lower resolution and lower signal to noise, but there's not an ugly gap in the middle of the image in any event. In addition, we have this strange problem of ADC bit flips, and this is a very long story. I could bore you for many hours on that, but it's getting worse it's gotten steadily worse over time. It's mitigated by imaging, by warming up the electronics to warmer and warmer temperatures, and then it returns good images. But it's gotten really bad in two of these, channel 1 of red 1 and red 3. And we keep finding new tricks to play to keep these going and keep getting our full swath width. Eventually, we're going to run out of tricks. And then once you stop imaging with red 1 and 3, why acquire data in 0 and 2? They're isolated. So we may then end up having a swath width of just 5 CCDs wide, so half of our original swath width. Now, if we have half the swath width, we can still accomplish all of our science, just less efficiently. We might need to take 2 or 3 images rather than 1 or 2 images to cover a target. So it's not, won't be the end of HiRISE, but we prefer to keep that wide swath width for as long as possible. And all of the CCDs have the spit flip problem to different levels, and so other units will have issues as well as we go on in time. All I have.